Our next topic is orthogonal subspaces. So let's say you have a subspace of the column matrices Rn, and let's call that subspace S. Now the set of all vectors in Rn that are orthogonal to every vector y that belongs to S is called the orthogonal complement of S, and we denote it with an S and a little perpendicular sign, and you can abbreviate that to S perp. That is, let's write this in set notation. S perp, the orthogonal complement of S, is the set of all vectors in Rn such that when I take the scalar product of x with y, I get 0 for all y in our subspace S. Okay? One thing to note is this space, the orthogonal complement of S, is actually a subspace of Rn. Let's check this. The first thing I need to show is that for all vectors a and b in S perp, we also have a plus b is in S perp. The second thing we need to check is that for all alpha scalars and any vector, I'm going to just call it b, in your S perp, you get alpha times b is also in S perp. Check these two things. If they both hold, then you have a subspace. So let's go with the first one. Okay, so we're going to let a and b be two vectors in S perp. We want to show, if we want to show that a plus b is in S perp, then we want to show that a plus b with y, the inner product of these, is equal to 0 for all y in your subspace S. How can we do that? Well, let's just consider the left-hand side of this. A plus b with y, this inner product. And this y is any y in your subspace S. Well, what is this by definition? This is a plus b transpose times y. And we know that the transpose distributes, so this is now a transpose plus b transpose times y, which is equal to a transpose times y plus b transpose times y, which is the scalar product of a with y plus the scalar product with b with y. And now we know, this is something we assumed, that a and b are in S perp. So then this is equal to 0 plus 0. Because if a is in S perp, this inner product is 0. And if b is in S perp, this inner product is 0. So then 0 plus 0 is 0, and we get that this inner product is equal to 0. So a plus b is in our space S perp. Let's show this second property. We have b is an S perp and alpha is a scalar. We want to show that alpha times b with y is 0 for all y in S. Okay, so we're going to consider the left-hand side of this. Alpha times b with y for any y in S, well, this is equal to alpha times b transpose times y. And when we take a matrix and we take the transpose of it, we can pull out the constant here, and this is just alpha times b transpose times y, which is now alpha times the inner product of b with y. But since b belongs to S perp, this is equal to 0. So alpha times 0, which is 0, and now we've shown that the inner product of alpha times b with y is 0. So the second property holds. So S perp is a subspace of Rn. Let's look at a real example of this. Here I have that S is going to be the subspace of R3, and it's just the span of E1, so 1, 0, 0. And I want to know what S perp is. Okay, let's write the definition again. S perp is all the vectors in R3, because this is a subspace of R3, so we're looking for all vectors in R3 such that the inner product of x with y is 0 for all y in S. So if y belongs to S, what does it look like? Y is going to be some number, we can call it alpha. Alpha here, 0, 0. Because it's some linear combination of this vector. So where alpha is just some real number. Okay? And what does x look like? Well, x is a vector in R3, so we can say x1, x2, x3. And the property we want to have is that when we take the inner product of x with y, which is x transpose times y, we want that to be 0. So what we're going to do is we're going to actually calculate this and see what restrictions we have on x1, x2, and x3. So the inner product of x with y is this thing transposed times y, which is just alpha 0, 0. We want that to be 0. And if you do the dot product, you just get alpha times x1 plus 0 is 0. Or alpha times x1 is 0. And this is supposed to hold for any linear combination you can come up with. Alpha could be 0, but alpha could also be anything else. So it could be 5, 10. So this needs to hold every single time. So that implies that for this to hold, x1 has to be 0. But that's the only restriction. We don't have any restrictions on x2 and x3. They can be anything you want to choose for this because we multiply them by 0, so they don't affect us getting 0 here. So that tells us x1 has to be 0, but x2 is free, and x3 is free. And if they're free variables, we can just call them s and t. So now let's write what x looks like and what S perp looks like. So x has to be 0, x2 is free, and x3 is free. So S perp is the set of all vectors that look like this, where s and t are real numbers. But can we find a basis for this space? Yes, because this is equal to s times 0, 1, 0 plus t times 0, 0, 1. So these two vectors are linearly independent, and you can see they span all these vectors here. So our basis is 0, 1, 0, 0, 0, 1, and S perp is the span of these two basis vectors. So any linear combination of these two vectors, if you take the scalar product of that vector with anything in S, which remember S looks like this, the span of these types of vectors, you're going to get 0. Okay? So suppose S and T are just two subspaces of Rn. We say that S is orthogonal to T, and we write this little perpendicular sign here. S is orthogonal to T if, well, what does it mean for 2 to be orthogonal? If for all cursive S and S, and for all T in capital T, we have that the inner product of S and T is equal to 0. Now you might be thinking, isn't this like the same definition as the orthogonal complement of S? And it's not quite the same definition. A special case of this is that S is perpendicular to S perp. So S is orthogonal to S perp. That's a special case. But we do have other cases. Let's look at an example of this. So before we said that when we had the span of this vector, S perp was equal to the span of these two vectors. But what if instead I take a subspace of this? Let's say I let T be the span of just one of these vectors, 0, 1, 0. Well, S is orthogonal to T because any linear combination of 0, 1, 0 with any linear combination of 1, 0, 0, those two vectors will be orthogonal. So for example, S is going to look like, let's say, A, 0, 0. T will look like 0, B, 0, where A and B are real numbers. And if you take the dot product of S with T, you'll get 0. So these two spaces, these subspaces of R3, are perpendicular, so they are orthogonal to each other. You could also take a linear combination of this one, or you could do something like, let's say, the vector 0, 3, 3. That's a linear combination of both of these vectors. It's 3 of this one plus 3 of this one, but you can see the dimension of this space is 1, this dimension of this space is 2, and this will also be orthogonal to any vector in S. So it will also be, S and T will also be orthogonal subspaces. So the biggest orthogonal subspace to S is the orthogonal complement. Here's a nice little fact. It says that if S is a subspace of Rn, then the perpendicular, the orthogonal complement of the orthogonal complement is actually S itself. Now we're not going to prove this. The proof is in the book if you'd like to check it out. One way is really easy. So what you need to do to prove this, just to give you an idea, you have to first show that S actually belongs to the orthogonal complement of the orthogonal complement, and this is actually easy. You just show that if you have an X and S, then this X belongs to this space. But the other way, so that's the first thing you need to do, but the second way is to show that this space sits inside S. and you'd have to let x be in this space, and you want to show that x belongs to S, that's a little bit harder to do, and you need to know about direct sums to do that. And we haven't discussed that part yet, but you could already show this way. And if you're curious on how to do the whole proof, you can read it in the book. But this is sort of like remember that thing we had with transposes? If you had a matrix, let's say S transpose, and then you take the transpose again, you get the original matrix. That's how you can think about this, sort of. It's kind of like the same concept. You have S perp, and then you take the perp again, and you get the original subspace. Here's another fact. If we have two orthogonal subspaces, then their intersection is only the zero vector. Let's prove this. So we're going to let S be orthogonal to T, and let's say that something belongs in the intersection. Okay, so if that's true, then because it's in the intersection, x belongs to S and x belongs to T. Let's consider the inner product of x with itself. What is that going to equal? Well, since x belongs to S, and at the same time it belongs to T, and these two spaces are orthogonal, then this has to be 0. Because you have something in S, something in T, and you're taking the inner product, so you must get 0. But on the left-hand side, remember x is a vector in Rn, so it looks like x1, x2, all the way to xn. And the inner product of x with x is x transpose x, which is x1 squared, x2 squared, and so on. But all of these numbers, when you square a real number, you're going to get a positive number or 0. And the only way for all of these, when you sum them, to give you 0 is if each one is 0. So this implies that x1 is x2, which is xn, which is 0. So that tells us that x has to be the 0 vector.